Hello everyone, I'm Zhang Leying from Shanghai Jiaotong University. Today, I want to share our recent work, Knowledge Distillation from Multi-Modality to Single-Modality for Person Verification. In this presentation, I will first present the research background. Secondly, I will introduce the proposed knowledge distillation method. Thirdly, I will give a description of our experimental details. Next, we will show the experimental results with related analysis and interpretation. Finally, we'll give a conclusion. Recent years, multi-modality systems, especially audio-visual systems, have gained a lot of attention. Previous studies in both neuroscience and computer science have also demonstrated that there is a correlation between audio and visual information. It is this complementarity between different modalities that makes the multi-modality system perform better compared with a single-modality system. However, unlike data in the lab, which can be prepared in advance, in some specific scenes of real life, it's pretty hard to access one's facial and voice information simultaneously. For example, when wearing masks to protect from COVID-19. Therefore, we hope that the efficient audio-visual system trained by the existing multimodal system can transfer the knowledge to the single-modality system so that it can adapt to more scenarios of real life and has good performance. Knowledge distillation has received rapidly increasing attention from the academic and industrial communities. By using this method, relatively small networks can achieve good recognition results under the guidance of more complicated models. However, most researches are limited to cross-model knowledge transferring. The study of using excellent performance of multi-modality system to teach the single-modality system is paid less attention. In our work, we explore the knowledge distillation from more perspectives compared with the standard one. To solve this problem, we have proposed our new knowledge distillation method for person verification task. Have a look at the whole process first. As the left part of this figure shows, we first train the audio system and visual system independently and extract its embedding. Secondly, thanks to the fusion model, we can get an efficient audio-visual teacher system, and we can extract the embedding of this fusion system. Thirdly, as shown in the right part, we apply the teacher-student method at 3 different levels: label level, distribution level, and embedding level. Finally, after training the model, we performed cause and distance scoring for evaluation. We first present our previous work on fusion models for training the audio-visual teacher system. This is a model proposed in our previous work, which uses a gate to control the information flow from face and voice modality. It can effectively combine the audio and visual information at the embedding level. Based on this model, our best multi-modality system achieves 0.514%, 0.375%, and 0.555% equal error rate on the 3 official trial lists of VoxCeleb 1. And it will be our teacher system in the following experiments. The single and multimodality systems are all optimized using additive angular margin, AAM loss, and we still choose the AAM loss in the following experiments. Based on this loss, we can obtain highly discriminative features for face and voice. To calculate it, a projection metric W is introduced. Each column of W can be used to represent the embedding center of one person. Then we will give a detailed description for the knowledge distillation from 3 levels: label level, distribution level, and embedding level. We first introduce the label level knowledge distillation loss. In our work, we prefer the KL divergence loss, which is also the most widely used loss in knowledge distillation works. Based on the projection metric W we have told previously, we can calculate the Pearson class posterior P in the first equation. For each input embedding E can be calculated. And the sigma is softmax function, T is temperature, fixed in our experiment. Embedding level knowledge distillation is a method directly used embedding from the audio-visual system to guide the single-modality system optimization based on cause and similarity. In this level, cause and distance can be a reasonable similarity metric between the embedding from teacher and student system. Maximum mean discrepancy, MMD, is a distance on the space of probability so as to determine if two samples are drawn from different distributions by projecting them on reproducing kernel Hilbert space. It is widely used in transfer learning, but also efficient in knowledge distillation. Here, we introduce MMD to guide the student model learn the embedding distribution of the teacher. The kernel function we chose for experiment is Gaussian kernel. Therefore, the whole loss function becomes the equation as follows. We explore their separate and combined effects by altering these hyperparameters. Then, we will describe our experimental details. For single-modality systems, the 40-dimensional F-bank is used as the input audio feature, and the facial image is sampled from videos in VoxCeleb 2. Data augmentation is not used for both audio and visual data. We apply ResNet 34. AAM loss is used to optimize both single-modality systems, where margin and scale are set to 0.2 and 32 respectively. The gated multimodal fusion system mentioned before is to fuse the audio and visual embedding. AAM loss is also used to train the fusion system, where margin and scale are set to 0.7 and 32 respectively. Next, we will show and analyze experimental results. Compared to the baseline system, all the visual systems after knowledge distillation from the audio-visual system achieve further improvement, and the result of MMD loss is 1.140%, 0.903%, 1.341% equal error rate on the 3 official trial lists of VoxCeleb 1, which achieves the best performance by simply matching the teacher and student embedding distribution in a batch. Besides, we explored combining different knowledge distillation methods together, and the results didn't show another improvement. The cause and similarity with strong constraint performs worse than the KL divergence and maximum mean discrepancy constraint. And this phenomenon is reasonable and further confirms that strong constraint is not suitable for multi-modality knowledge distillation, because we think there is a large gap between audio and visual information, and we can't enforce embedding from teacher and student exactly matching. When it comes to the audio system, all experiments achieve great improvement compared to the baseline on Vox 1.0, and the improvement on Vox 1E and Vox 1H is not so obvious. Embedding level distribution based on cause and similarity performs worse among all these methods, which is consistent with our findings in the Vero system. To further prove the learning quality and give analysis of multimodality knowledge distillation, we analyze the knowledge learned by the Vero system from the teacher based on different system score on Vox1e. In this figure, 5,737 trial pairs originally misjudged by the Vero baseline system, and then corrected by the knowledge distillation. Surprisingly, 4,877 trial pairs of them were correctly predicted by the audio system baseline, accounting for 85% of knowledge learned from teacher system. For the audio system, 1,945 trial pairs originally misjudged by Vero baseline and then corrected by our method. There are 1,862 trial pairs of them were correctly predicted by the audio system baseline. However, the total amount of knowledge learned by audio student system is much smaller than that learned by the Vero student system. To further explore the relationship between single-modality system and multi-modality system, we use the Pearson correlation, where a larger value means stronger correlation. We find that the PCC, the Pearson correlation coefficient, between Vero and audio embedding before fusion and audio Vero embedding equals to 0.079 and 0.007 respectively. We also found that when utilizing cause and similarity for knowledge distillation, after teacher-student training, the cause and distance loss of Vero system has dropped to 0.4217, but the cause and distance loss of audio system is still 0.583. These phenomena shown above indicate that it is more difficult for audio system to approximate embedding of teacher system, which may be not a good teacher for audio system. Finally, we will give a conclusion. We explored and compared our knowledge distillation method at different levels for the audio and Vero system. Results show that the Vero system achieves 10% equal error rate relative improvement on the VoxCeleb 1 evaluation set. For audio student system, the improvement is mainly reflected in some evaluation trials, and we analyze the reasons in detail. In our experiments, we also found that most of the performance improvements came from the knowledge already learned in the other modality, which indicate that the teacher system really leverages information to help the single modality system. That's all. Thanks for listening.
Thank you. Any questions in the room? Okay, I have one question. As far as I understood, to your audio-visual model, you have trained your audio system first and then video first, and then in your fusion model is trained for fusion, and the parameters of audio and visual are the same, right? You're not retraining them.
No, for the fusion, we directly using the embedding extracted from the Vox system and audio system, and these two embeddings are the input of our fusion model. Yes, they're equal in this. They're equal input for this fusion model.
So what if you jointly trained both audio and visual at the same time, or just retune the parameters from audio and visual? Then in your test, you just extract the embedding from the audio or video and use that embedding instead of teacher-student model?
Well, we haven't
because
tried.
In that case, then you're sharing the information when you jointly train the whole network at the same time.
Yeah, I think that's a good suggestion. And we haven't tried the joint training in the previous studies, but I think it can be it can be efficient, and we will study them in the future.
Okay. Any more questions? Yep.
Hi, thank you for the presentation. Very interesting because I'm working on similar topics for emotion recognition with a student. My question is, you show a formula where the losses are, it's a weighted sum of the losses. But maybe I miss it. What are the weights for the different losses? Show the formula where you have alpha, beta, and gamma. And then, okay, that's like a comment. Basically, you get most of the improvement when you align the embeddings. And that's, I mean, makes sense because then the classifier is the same as far as I understand. So when the embeddings are aligned, of course, and the labels are the same, the classifiers will be probably the same, right?
Well, in our experiment, we have adjusted these hyperparameters, and the results shown above is the results that we've chosen the best performance after altering these hyperparameters. Not to say that all the losses, like the losses for the distribution level and for the causing level, are exactly the same. Now, not to say the hyperparameters are the same.
Any more questions? Okay. Regarding these hyperparameters, alpha, beta, and gamma, how did you tune them? Was that time consuming, or how are you sure you have chosen the best parameters? Because your final combination are not better than every single system.
Well, we first trained those single losses. That is to say, we first explored the separate effects of each level knowledge distillation. And after finding the best hyperparameter for each loss, and we combined it together, and we made some other alternations, but not so many. And in our paper, we have mentioned that all the results shown above is the best result, but the hyperparameter chosen for the combination of different losses are basically based on the best hyperparameters for separate loss training.
But this alpha, beta, and gamma you use for training the whole system together, right?
Could you please repeat your question?
Your final loss, when you have combining all the loss together with the alpha, beta, and gamma weights, this is the case that you train all together, right?
Yeah.
Then for the best combination, you need to tune this alpha, beta, gamma maybe several times. My question was that it was not so time consuming, or?
It's not so time consuming because we've chosen the hyperparameters basically from 0.5 to 1.5 for each hyperparameters, and we have tried several times, but the results are basically pretty stable, and we have chosen the best to shown in our paper.
Okay, so I think we are done, and let's thank the speaker again. It was the last speaker, and then thank you for attending the session.